Welcome, my name is 𝘁cie𝗶𝗰𝘀. In the next part of this introduction to confidential computing with SCONE, I will talk about a threat model that is underlined in SCONE. So in the threat model, we need to answer certain questions. What assets do we want to protect? What are our adversaries? What are potential attack points on our application? And as always, in confidential computing, our focus is on protecting applications. So that means the code, the data, the secrets of our application we want to protect against unauthorized entities. And these entities might use different ways to attack our application. And they might log in as root users and might be able to read certain configuration files or modify them. They might roll back time or roll back the disk state. So they might use an old backup of an old database state and put that in the system. Or they might have insider information that allows them to access our system. There might also 𝘁cie𝗶𝗰 attacks or impersonation attacks where they try to impersonate other services or users. They might use side channels. So that means using information by just observing, for example, the cache of the CPU. Or they might actively change the voltage of the CPU to cause wrong execution that can be used in turn to derive some secret information from our application. So there is a long list of potential attacks on our application. And so what we need to look at is the threat model. So what are the threats that we need to defend against? There might be also threats that we say it's unlikely that we need to defend against these threats, depending on the criticality of the application and the data code and secrets that we want to protect, and also kind of the resources that we have to protect against these threats. So the threat model that we have, that we use in SCONE is based on a threat model by Intel. So the link to the Intel threat model is here on the bottom of this slide. And as a summary, we look at 8 different threats, and I will briefly introduce them on the next few slides. So here's just a summary of the threats. So we first look regarding threats from unprivileged software that might run on the same hardware or even the same VMs that we run. There might be system software adversaries, or the operating system or the hypervisor is trying to attack our application, or there is some higher privileged code that tries to access our our application, or the boot up or the startup code that runs on the system. Then traditionally we need to take care of network adversaries that try to attack our application, while here A1, A3, the adversary has access to our computers already. Then there might be a side channel that we need to take care of, so that the adversary observes or can observe the cache behavior and derive some secret information from that cache behavior. There might also be some simple hardware adversaries that try to access the main memory by, for example, taking out the memory chips, deep freezing them, putting them in a different computer, or changing the time or the disk state to a historic state to get access to our data, code, and secrets. And also, so the rollback state adversary that is not in the Intel threat model, that is an addition that we have here. And moreover, the 𝘁cie𝗶𝗰 adversary is an adversary that knows exactly what kind of dependency we have in our application and tries to attack our application based on published vulnerabilities of these dependencies. So let me zoom into the different threads A1 to A8 and talk a little, or give you a little bit more details for each of them. Let me start by introducing the unprivileged adversary. So here we assume that an adversary can run normal user code on the same server or the same set of servers that our application runs. In a cloud setting, this might happen, say, in a cloud, computers are shared, the different applications are typically isolated using virtual machines. And there, it's actually quite difficult for an adversary to be co-located to an application that that adversary wants to attack, because there are so many servers, typically thousands of machines potentially, and being co-located on the same physical server is difficult, and all these co-located applications will be in virtual machines, so they are sandboxed, and the adversary would need to first break out of that sandbox. So the virtual machines are part of this system security I talked in an earlier part of this introduction. And so from that perspective, it's really difficult from being a unauthorized, unprivileged adversary to break out these sandboxes. Of course, not impossible, so there are examples where one can elevate the privilege to become from an unprivileged user, a privileged user, and breaking out of this sandbox. In this case, the adversary would become a system adversary. So a system adversary has root privileges on the operating system or the hypervisor, and is in this way authorized to read the main memory of applications. So that means an authorized system adversary has the privilege or sufficient privilege to dump the memory, and if the memory of the application is not additionally encrypted using a concept like an enclave, then sees the in plain text, the code and the data and the secrets of that application. An alternative of dumping the memory is, of course, using the debugger and attaching to that process and accessing the main memory via the debug interface that is provided by the operating system. And the debug interface allows us to not only read the data and code and secrets from the application, but also modify that. So one could change that during the runtime. So it is important that if we have a system adversary, that even if we have encrypted memory, that it's not possible to attach the debugger to an application to gain access to the secrets of that application. So we have to be able to prevent that there is kind of a backdoor into that application. So debugging needs to be prevented of confidential applications. So now the question is, why should we assume that that we have a system software adversary? So one reason could be legal, because our cloud provider might be required to give access to the data that is processed on the infrastructure. So there might be just legal requirements from wherever jurisdiction that cloud provider is in. It might also be that the employee of the cloud provider might be required to give access. So that employee might be of a certain nationality, and that nationality requires that employee to follow the laws, even if that employee is maybe working in a different country. So kind of his or her home nationality might require that employee to grant access to a different country. There might also be liability reasons. Maybe it's too expensive to err on the threat model side. So we want to protect, as an application owner, we want to protect us against data leakage, or maybe as a cloud provider, I want to make sure that if data is leaked by my employees, that this is not, or I want to prevent that data is leaked by some of my employees, and so reduce the liability that I have as a cloud provider. Even if we have access control mechanism, we have the potential of insider attacks, so there can always be employees that are motivated to share data for different reasons, monetary reasons, or there might be some pressures that apply to these users. And so therefore we have to make sure that we protect the employees by not being able to be pressured to grant access to certain data, by not allowing them individually to grant access or having access to certain data. Another reason why we want to assume system software adversaries is that we have a certain software complexity. So the system software is quite complex. There are hundreds of potential attacks on the operating system, the hypervisor, and it's often really difficult to detect these bugs and fix them. So from that perspective, just looking at the complexity of system software, there will be always some gaps in the protection by assuming that an adversary can exploit these bugs and gain access as a system software adversary that we need to expect and protect against. Also, there are certain hardware problems that we need to address. So there's a base management controller, there's certain firmware that might be buggy, and that might give adversaries root access on our systems. And so therefore, there is a good reason why we assume that adversary could have root access on the system. There is more privileged code that can run on hardware. There might be some startup code and system management code that the adversary might gain access and gets privileged access to the system. And we assume in the context of confidential computing that this might be the case, so that adversary have gained access to the startup code and the system management code, and we need to protect ourselves against those adversaries. Also, adversaries will definitely try to attack our application via the network. So even if there are firewalls, there will be attacks on our individual services from an adversary, try to connect to our services and try to exploit our applications using potentially vulnerabilities of the services via the network. Also, we assume that there are side channels, so that an adversary might have lots of interest in getting access to our data or some of the data or secrets, and tries to monitor our application and try to determine some secrets using, for example, side channel attacks of the cache, trying to see if the cache behavior can reveal some of the secrets. There are lots of papers in this domain that try to use side channel attacks to gain access to some of the secrets of an application. In some later section, I will show how we can address some of these side channel attacks. There are more adversaries that we need to expect. So we expect in this context of SCONE simple hardware adversaries. So this simple hardware adversary can remove DRAMs, might have some hardware debugging tools, can listen to buses, so can do certain things with the hardware. But it's only a simple hardware adversary. We don't have a advanced. We also need to consider that the adversary just might get access to some old hardware, some old CPUs, some TPM that is not used anymore. And we have to actually take care of the decommissioning of hardware from our system. Another attack that or adversary that we need to consider are the rollback state adversary. This is not part of the original Intel threat model. This is something that we extended, did an extension for SCONE. And here the assumption is that the adversary can take snapshots of our disk and then roll back the disk state to an earlier state, for example, to hide certain transactions that are which state is in the kind of on disk, and try to roll back a T state. The other thing that the adversary could do is roll back the firmware of the CPUs, so that and also architectural enclaves, such that we have old firmware, old enclave code, such that the adversary could use that to attack our system. One way of using that is that the attacker or the adversary could actually take a copy of our enclaves, deep freeze it, keep it there, and then wait until our until vulnerabilities are known, and then attack the system by unfreezing it and use the knowledge about the vulnerability to attack the system. So in this rollback state adversary, we need to take care of or be able to take care of in case that is considered by application a potential threat to the application. Something that is similar to the last adversary is the following. We need to expect that the adversary knows all the vulnerabilities of all the dependencies of the services that are in this application that we want to protect. So we need to make sure that we know if there are vulnerabilities and know that we have to update certain applications to protect against adversaries that will know specific vulnerabilities and exploit them. So there are, of course, limits to what threats we can cover. So right now there is no built-in protection against skilled hardware adversaries. So in hardware adversary, they can reverse engineer the CPUs and the fuses on top of that are in the CPU that are used to derive secrets. We don't have protection against this. That would require additional hardware or physical security at least. And we also cannot protect against authorized adversaries that might have insider knowledge that allows them to derive keys like the seal keys by the CPUs.